In chapter 13, we discussed the chi-square test. It has three test procedures. We discussed the first one, the goodness of fit. And today, the second one is the independence test. And the third one will be the homogeneity. It's a homo. Before, in the goodness of fit, we had a sample, and we had previous proportions. So we want to test if they have the same distribution. It's like as the one sample t-test. You know, the one sample t-test, the null hypothesis was as mu is equal to the mu zero. You know, actually the mu zero, that is the initial setting value for the one sample. So in the goodness of fit, we had the one sample, and there was the target is a proportions. So it's not exactly same, but I can compare the one sample t-test. But in this case, we consider the population mean, unknown population mean. But now in the chi-square test, we are using the counts, the frequencies. So in the goodness of fit test, the chi-square test is kind of we can compare with the one sample t-test. But the independence test, there is two categorical variables. One is the marital status and the drink. So now I can compare to the two sample t-test. Actually, we compare the two population means. So exactly it will be the homogeneity. The homogeneity test is later, but the independence test and the homogeneous test is the same procedures, but only the difference is the data structure, right? So later we can take the later we are going to discuss the homogeneity, the test, but they are same procedures. So now we have the categorical variables. So here is the procedures. Here is the independent test. So first of all, we can state the null hypothesis. The null hypothesis is the two variables are not associated. So simply I can say they are independent. Independent means it's not related. And alternative hypothesis is that they are related, absolutely. And the second step, the test statistic, that is looks the same as the test statistic in the goodness of fit. So we observed one minus the expected one, take the difference square over the expected one for each case, and just to take the summation. So that will be the test statistic, the chi-square. And step 3, we can take the p-value from the right tail, but the degree of freedom for the chi-square distribution is not just c-1, but it is a c-1 times the r-1. So the number of columns is number of rows with just one of, then multiplication, that will be the degree of freedom. And we are going to make the decision and the conclusion. It's the 5 steps, we can do the independent test. So let me go back to the example here, right? So here is the observed one, that is the observed point from the 1,772 samples. So now we can take the expected value. We need the expected frequencies. Here's a formula. Is how can we get the expected frequencies. We need the R and C. The R is the row total. It's actually this one. Let me take the expected frequencies here. Then we can take the subtotal, the row total, and C, the column total. Then take the multiplication. So that will be 354 times 5 is 90. Then divided by the sample size. It's actually 1772. That is the sample size. So divided by 1772. When I take the another one, if I want to take this expected count, then let me take the capital R, the subtotal, and another capital C, the subtotal. So it will be 143 times is 957 over it's a 1772. So you can take each the expected count, then it will be 117.87, and the next one will be 191.18, and it's a 44.95, and 390.56, and 633.50, and 148.94, and 47.61, and this one will be 77.23, and 18.16, and 33.96, and 55.09, and the last one will be 12.95. So it's not only the observed one, but also when you take the sum up, that will be 590. And the second column, the summation of the 4 expected frequencies, that will be 957. And the last column, the summation, that will be 225. It's not only the column wise, but also the row wise. Yeah, we can take the subtotals, right? So you can check as by yourself if you get the expected frequencies correctly. Then now it's almost the same way. We can take the test statistic. So now it is the expected one. So O minus E difference square over E. That means take the 67 observed one minus the expected one, 117.8. Then take the difference square over 117.8. So for each cell, you can take the difference, you can take the square, you can take the division. So totally, it's a 1, 2, 3, 1, 2, 3, 4. You can take the, it's 3 by 4, 12, the partial chi-square. I can say it is the partial chi-square. And you can take the sum up, the 12, the partial, the chi-square. Then you just take the sum up, it will be 94.27. That will be the chi-square, the test statistic. Then now, from the chi-square distribution, we have 94.27. It's absolutely, the 94.27 is big enough. So we can expect the p-value will be very small, but we need the probability from the function in your calculator or Excel, but we need the degree of freedom. I told you the number of rows minus 1, So it's a 1, 1, 2, 3, 4 minus 1. And the C minus 1, the number of columns is 1, 2, 3 minus 1. Then times. So that will be 3 times 2, 6. So the degree of freedom will be 6. So with the degree of freedom 6, it's bigger than 94.27. The p-value will be almost 0. Then finally, the decision will be reject the null hypothesis. So finally, it's a reject the null hypothesis because the p-value is almost 0. Let me set alpha equal 5%. Then we can reject the null hypothesis. So conclusion will be the two variables are associated. They are related. The drink is per month and the marital status, there is a relationships. So it's more details. We can expect the observed one and the predicted one. It's actually we observed is only 67, but when we expect the frequencies under the null hypothesis, that means when we assume they are not related, they are independent, then we can expect it must be 117. But we observed is much less. And let me take it is almost the same, right? But let me take the difference. Here is the 85, but here is 47. We observed is much more. And here is a 7, and there is a 18. We expected is twice more, right? So as a one by one, we can compare. And some of them is much bigger observed than expected one. Is sometimes is almost the same, and sometimes is less. So as because of that, they contribute to get is a bigger test statistics, and finally the smaller the p-values. So it is the procedures for the chi-square, the independence.